Hi everybody. This is a little mini lesson on electromagnetic waves and photon production and how we can get different wavelengths of light produced by a hydrogen atom. First of all, let's look at the electromagnetic spectrum from the biggest wavelengths to the smallest wavelengths. And you can see here that I have a little spectrum drawn out here from radio waves, which happen to be the biggest, to gamma waves, which are the smallest. The radio waves range, there's a wide range, but let's just say that on the order of 100 meters, give or take a lot. Okay, all the way down to a little bit less than a meter. So there are some radio waves that could be in the hundreds and thousands of meters. Microwaves, like what you'd have in your microwave oven, they're about a centimeter or a hundredth of a meter. Infrared, then visible light, then ultraviolet, X-rays, and gamma waves. Notice the gamma waves 10 to the negative 12th meters for their wavelength. Incredibly small. Now as we go down and get smaller and smaller in wavelength, the frequency happens to increase. Okay, so the frequencies are actually inversely related to the wavelength. So if we have a big wavelength over here, we have a little tiny frequency. We have a small wavelength for gamma waves. We have a really big frequency. And as we'll learn in a minute, the bigger the frequency, the more energy a photon of electromagnetic energy has. If we look at visible light, and light is usually referred to the visible part of the spectrum, the biggest wavelengths of visible light are in the red range, and then the smallest would be in the violet range. So reds would be, 7 times 10 to the negative 7th meters, or 700 nanometers or such, and then all the way down to violet, which is in the order of about 4 times 10 to the negative 7th meters, or 400 nanometers, or billionths of a meter. How about the speed of these electromagnetic waves? Well, in a vacuum, they all have the same constant speed of approximately 3 times 10 to the 8th meters per second. That's in a vacuum, though. Now, if we put that in more familiar terms, like in miles per second, that's 186,000 miles per second. Of course, then, if the electromagnetic waves are traveling in materials such as water or glass or a diamond or something like that, they slow down significantly. You can see that in water, light waves and other electromagnetic waves only travel at 2.25 times 10 to the 8th meters per second, and in a diamond they travel much slower, 1.2 times 10 to the 8th meters per second. You might ask, in air, though, air doesn't slow electromagnetic waves down very much, so we can treat anything traveling through air, for our purposes at least, as having an electromagnetic wave speed of 3 times 10 to the 8th meters per second. Now if we look at a little further in terms of how electromagnetic waves are propagated, they're propagated basically because of electric field and magnetic fields. Okay, so if this little thing here is an antenna, let's say a radio transmitter antenna, and it's sending out electric fields are going back and electric fields are building up and shrinking and going back and forth because of an alternating current here, and magnetic fields are perpendicular to that. Those electric fields and magnetic fields radiate out into space, as you can see here in my drawing. Okay, the electric fields are perpendicular to the magnetic field. So as the electric field builds up, a magnetic field is automatically generated that's perpendicular to that electric field. As a magnetic field is set up, an electric field is automatically generated by that magnetic field perpendicular to it, and so on. And so basically the electric field generates a magnetic field, and the magnetic field generates the electric field, and they just keep propagating through empty space like that, and they build upon each other. They propagate. So the direction of propagation would be to the right in this case. So that would be traveling out in space. So if we had something, some radio station which transmitted a Jack Benny show or something like that 80 years ago on the radio, now that those radio waves are still traveling out in empty space outward in the universe, and those waves are now at about 75 light years away from us. So they're still traveling out there. They're continuing to propagate each other, even though the source of the electromagnetic wave, the original transmission antenna, is long gone. It's no longer transmitting the signal, but the electromagnetic waves are still propagating because the electric field propagates the magnetic field and vice versa. Now let's take a look at a famous relationship. We'll call it the wave speed equation. V standing for speed or velocity. We can also use C, which stands for the speed of light or speed of electromagnetic waves in general, and that's equal to the wavelength lambda times the frequency. Let's look at an example of a problem. Okay, calculate the wavelength lambda of the FM radio frequency 93.3 megahertz. Capital M stands for megahertz is cycles per second. That's 93.3 megahertz. Now this is the carrier wave frequency. That's not the frequency of the sound waves that are coming out of the loudspeaker. It's just the carrier wave. Our ears have no way of hearing that high of a frequency. We can only hear from 20 hertz to 20,000 hertz at best. Okay, so what do we know so far? We know that the frequency of the radio station is 93.3 megahertz, which translates into 93.3 times 10 to the 6th waves per second. We have to convert it out of mega and just get it into hertz or waves per second. So 93.3 times 10 to the 6th waves per second. So this is in the form that's compatible with our meters per second. C, or the speed of light, is 3 times 10 to the 8th. Even though it's traveling through air, we're still going to make the assumption that it's about the same speed. It's not significantly slowed down by the air. Okay, the formula for wave speed, whether it's electromagnetic radiation or whether it's a mechanical wave like sound waves or water waves, it's still wavelength times frequency. Rearranging it to solve for wavelength, we get wavelength lambda equals C over F. We'll plug our wave speed in of 3 times 10 to the 8th, that's the speed of light, divided by the frequency, and we get 3.22 meters for each wave, or just meters. So that's the wavelength of those electromagnetic radio waves that are transmitted out from that radio station. If we want to visualize that with a little cartoon, here's the radio transmitter transmitting radio waves out in all directions. If we just look at the waves going to, like, your radio, for example, we can see from peak to peak or trough to trough, the wavelength is 3.2 meters, or about a little over 3 baseball bats in length. Now there's another very famous equation. It's called Planck's equation. It was developed by Max Planck and also Albert Einstein. And this basically shows the relationship between the amount of energy in a little quantum or packet of light energy known as a photon. This sets that equal to h, some constant, times a frequency. So the energy of a photon, or quantum of electromagnetic energy, is equal to h times f, where h is Planck's constant. It's a constant value, as the name says. It doesn't change. If you want to deal with joules of energy, then we have to use this top version of Planck's constant, 6.63 times 10 to the negative 34th joule seconds. On the other hand, if we're going to deal in energy units called the electron volt, then we would have to use Planck's constant in that form, which is 4.14 times 10 to the negative 15th electron volt seconds. In our class, we have been already using electron volts as a unit of energy. when we were dealing with nuclear, so this shouldn't be any big surprise. Here's a sample problem. Example, what is the energy in electron volts of a photon emitted from the previous radio station? So, what do we know? We know that the frequency of that radio station was 93.3 times 10 to the 6 waves per second, or hertz. That's the compatible unit. Planck's constant, since we want it in electron volts, we're going to use the form of Planck's constant given in electron volts, 4.14 times 10 to the negative 15th electron volt seconds. Now we'll use that famous Planck's equation, E equals hf. And by the way, the bigger the frequency, the bigger the energy. That's a good way of looking at that, right? Okay, plugging our numbers in. I'm not going to even mention them. You can see there the numbers. This is Planck's constant. This is the frequency in compatible form. Multiplying it out, we get 3.86 times 10 to the negative 7th electron volts of energy. And electron volts, what's the symbol for it? Little e, big V. Okay. Well, so far then we know how to find the energy of a photon if we know what the frequency is. Now let's take a look at how light is produced from an atom. Light is produced by what Paul Hewitt, a physicist and textbook writer and famous teacher, he used this term, Gulp-and-Burt process. Light is produced by the Gulp-and-Burt process in atoms. Basically, what does that mean? That means if, let's say this is an atom, here's the nucleus in the middle with various energy levels that electrons can hang out in. If this atom absorbs an appropriate amount of energy that happens to match up with the difference in energy between this first energy level and, say, this third one, then that electron would get excited and jump out to an excited state, from its ground state to an excited state. That's only a temporary measure, though. The electron is unstable. It might snap back one energy level or more. Let's say it snaps back down from an excited state down to a less excited state. When it does that, it's going to release that same amount of energy, that's the difference between those energy levels. It's going to release them in the form of a packet of, or quantum of energy known as a photon. Okay, so here's this little squiggly arrow represents a photon. So the atom then gulps in an appropriate amount of energy and burps out a photon of energy. Gulp and burp. The electron jumps out to excited state. It goes back down to a lower energy state and burps out then that energy. Okay. Let's look at the hydrogen atom now for the rest of this mini lesson. If we look on the periodic table, the first ionization energy for hydrogen atom, it says on your periodic table is 13.6 electron volts. Okay? So that, in other words, if you wanted to knock an electron out of the hydrogen atom, you would have to apply 13.6 You'd have to apply 13.6 volts of energy, of electric potential, in order to do that. So that'd be about the amount of voltage in a car battery. Okay. So, and ionization simply means that an atom becomes an ion. So it's going from its neutral state where there's zero charge, one proton and one electron adds up to zero for the net charge. Once it loses an electron, though, that hydrogen atom is going to have a charge of +1. It has become an ion. So if we look at our little diagram here that I'm pointing to, let's say hydrogen's electron is in its lowest or ground state here. But let's say that this atom absorbs 13.6 electron volts worth of energy. Boom. That's going to cause that electron in its ground state to move farther and farther and farther and farther and farther and farther, and it's not coming back. It got knocked out of the atom. It's like They hit a home run. It's over the fence. How much energy was required to do that? 13.6 electron volts to knock it from its n equals 1 ground state all the way out of the atom. You can see here, though, that if the electron would happen to be in level 2 or level 3 or level 4, it's not as far away from being knocked out, is it? So it's actually easier to knock the electron out from one of these energy levels compared to the first energy level. Okay? So it's like if you're closer to the fence, you can hit it over the fence easier. Now, the way to figure out what the amounts of energy needed to do that for those outer energy levels is to use what's called an inverse square law. We'll use a 1 over n squared relationship where n is just the energy level. Energy level 1 is n equals 1, energy level 2 is n equals 2, and so forth. By the way, I drew 7 energy levels here. There are more, and also the energy levels as you go out are actually squeezed tighter together, not like this cartoon version here. Okay, I drew 7 because 7 is a nice number because it corresponds with the 7 rows in the periodic table, and we'll get to that some other time. Okay, now, so let's use that inverse square law. If the electron is in energy level n equals 2, then the energy required to knock the electron out of the park, if you want to call it that, is 1 over n squared, or 1 over 2 squared, which is 1/4. And what's 1/4 of 13.6? If we take 1/4 times 13.6, or in other words 13.6 divided by 4, we get 3.4 electron volts. Okay, so for n equals 2, instead of 13.6 electron volts like it is to knock it out of energy level 1, it's 3.4 electron volts. Let's try another one. What if the electron is already in n equals 5, and we want to knock the electron from n equals 5, excuse me, the light just went out, from n equals 5 all the way out, away from the atom to ionize it? How much energy would it take to do that? Well, we'll use that 1 over n squared law again. So it takes 1 over 5 squared, or 1/25th the energy. So if we take 1/25th times 13.6, we get 0.544 electron volts of energy needed to knock it out of the park from the 5th energy level out. Okay? So with those concepts, we can now determine the amount of energy associated with each of the energy levels in the hydrogen atom. Okay, so that's not bad. I guess we could, let me get that paper back that I had just before, and I can write those down. So we have 13.6 electron volts associated with our first energy level, 3.4 electron volts. How about for level 3? If I use 1 over 3 squared, or 1/9 of 13.6, that comes out to be 1.51 electron volts. How about n equals 4? 1 over 4 squared, or 1/16 of 13.6, is 0.85 electron volts. The 5th energy level we already know, 1/25th, 0.544. How about the 6th energy level? 1 over 6 squared, 1/36th of 13.6. So that's 0.377. And then the 7th energy level, 1 over 7 squared, 1/49th of 13.6 is 0.278 electron volts. So now we know, at least for the first 7, we could do it for 8, 9, and 10 or whatever, also energy levels. But for our first 7, we know what those energies are for each level. 13.6, 3.4, and so forth. So we can determine the energies associated with each level in the hydrogen atom. Okay? Using this concept now, we can calculate the frequency and the wavelength of photons emitted from a hydrogen atom. You've seen the electromagnetic spectra using spectroscopes looking at the hydrogen gas in one of those Geissler tubes. You've seen the spectrum. How does that spectrum, the emission lines, get produced? Well, let's take a look at an example. Okay, let's say that we have an electron in the hydrogen atom that's at n equals 5, and let's say it jumps down to level 2, n equals 2. What is the wavelength emitted from hydrogen when its electron jumps from n equals 5 to n equals 2? And we're worth wondering, what is the wavelength of this photon that's emitted? Okay, so let's take a look at the solution. Okay, using our 1 over n squared idea and hydrogen's first ionization energy of 13.6 electron volts, let's look. What's the energy for n equals 2? It's 1 over 2 squared, or 1/4 of 13.6, which gives us 3.4 electron volts. We do the similar procedure for n equals 5. That's 1 over 5 squared, or 1/25 of that, of 13.6. We get 0.544 electron volts. Now, if we take the difference in those two energy levels, that difference in energy, or delta E, represents the amount of energy released in the photon, in that photon. So delta E is the difference, or we'll just take the absolute value, 3.4 minus 0.544. We get 2.856 electron volts. So this is the energy of the photon. But I asked you, what is the wavelength, not the energy. So we have to go a little bit further. Okay, so we need to find the frequency first. So to find the frequency, we'll use Planck's equation, E equals hf, rearrange it to solve for frequency, that's E over h, and plug our energy in of 2.856 electron volts divided by Planck's constant in terms of electron volts, which is on a previous page, 4.14 times 10 to the negative 15th electron volt seconds. When we divide that out, we get the frequency of 6.89 times 10 to the 14th cycles per second, or hertz. But it didn't ask for frequency, it asked for wavelength. So we need to go one step further and use our wave speed equation. Speed of light equals wavelength times frequency. Rearranging for lambda, or the wavelength, lambda equals c over f. That's 3 times 10 to the 8th meters per second over the frequency, which we just found. And we get the wavelength is 4.35 times 10 to the negative 7th meters, which corresponds to 435 billionths of a meter, or nanometers. And that, you may recall using your spectroscope, would be a violet color. That's violet, okay? Whereas if it was about 700 nanometers, that would be reddish. Okay? So there you have it, my friends. Thank you for watching, and see you later.